Hello, everyone, and welcome to the second week of my Astronomy 101 public talks. So, as advertised last week, tonight's talk is about what you can see in the night sky and explain the motion of objects in the night sky. Tonight's quote is a bit more cheerful than last week's. It's from Huckleberry Finn by Mark Twain. We have the sky up there all speckled with stars, and we used to lay on our backs and look up at them and discuss about whether they was made or only just happened. So today we take for granted that we live on a small planet orbiting an ordinary star in one of many galaxies in a very vast universe. But this fact is not obvious from a casual glance at the night sky. And we've learned about our place in the cosmos only through a long history of careful observation. So we'll take this time to discuss the major features of the night sky and how we understand them in light of our current knowledge of the universe. So if you were to go outside tonight, shortly after sunset, the sky would fade to darkness and stars would start to slowly fill the sky. On a clear, moonless night, far from city lights, more than 2,000 stars may be visible to your naked eye, along with the whitish band that we call the Milky Way. As you look at the stars, your mind may group them into patterns that look like familiar shapes or objects. If you observe the sky night after night or year after year, you will recognize the same pattern of stars. These patterns have not changed noticeably in the past few thousand years. People of nearly every culture gave names to those patterns they saw in the sky. We usually refer to such patterns as constellations, but to astronomers, the term has a more precise meaning. So a constellation is a region of the sky with well-defined borders. The familiar patterns just help us locate these regions. So just like every spot in the continental United States is taken up by a state, is owned by a state, every point in the sky belongs to some constellation. So here you can see some of the winter constellations you might see if you were to go out tonight, March 7th. You can see Orion, Canis Major, the big dog, and Canis Minor, the little dog. Some of their brightest stars connect together to form what is known as the asterism called the Winter Triangle. Those stars are Betelgeuse in Orion, Sirius in Canis Major, and Procession in Canis Minor. The Winter Triangle is an asterism, not a constellation. There are only 88 official constellations. Anything else is an asterism. But I want you to notice that the patterns on the sky are bounded by these red boxes. Those red boxes actually define the constellations. And those constellations were defined in 1928 by members of the International Astronomical Union. There are 88 of them. Since most of the IAU members lived in Europe or the United States, they chose names familiar to the Western world. That is why the official names for constellations visible in the Northern Hemisphere, which you can see here, can all be traced back to civilizations of the ancient Middle East, while the Southern Hemisphere constellations carry names that originated with 17th century European explorers. So in the Northern Hemisphere, you have a lot of constellations that are associated with Greek myths, like Andromeda, Cassiopeia, Orion, Perseus, Cygnus, Aquila, Ursus Minor and Major. All of these have Greek myths, and if you trace those Greek myths back further, they all have Babylonian or Sumerian myths associated with them. Meanwhile, in the Southern Hemisphere, there are still some Greek myths. The sky has shifted, so the ancient Greeks could see a little bit more than we can in the Northern Hemisphere today. But most of them are named for either the animals or locations that European explorers found when they traveled to the Southern Hemisphere, or scientific instruments of the scientific revolution. So that's why we have stuff like telescopium and microscopium, the telescope and the microscope. We have things like Phoenix, the Phoenix, Mensa, which is Latin for table, named after Table Mountain in South Africa. Things like Grus, which I believe is a fly, and Indus is an Indian person. Whether that means a Native American or someone from the Indian subcontinent is up for debate. That's why you see much more interesting names that we in the Northern Hemisphere are certainly not as familiar with. I do encourage you to go outside tonight or whenever it's clear in your area and take a look at the night sky. Use a star chart, use an app that you've got on your phone, or even just planetarium software you've got on your computer, because recognizing just a handful of these constellations will make the sky feel less foreign. It will make it feel like your own neighborhood. So these stars in each of these particular constellations appear to lie close to one another. This is what you should be thinking about when you're looking up at the sky. But the stars in each constellation are probably much further apart in reality because they may lie at very different distances from Earth. So you can see that in the figure on the top right. This illusion occurs because we lack depth perception when we look into space, a consequence of the fact that stars are just so far away. The ancient Greeks mistook this illusion for reality, imagining the stars and constellations to lie on a great celestial sphere that surrounds the Earth. We now know that the Earth seems to be in the center of the celestial sphere only because it is where we are located as we look into space. Nevertheless, the celestial sphere is a useful illusion because it allows us to map the sky as seen from Earth. So for reference, we note 2 special points and 2 special circles. So the north celestial pole, which is up here, is the point directly above the Earth's north pole. Similarly, the south celestial pole is directly above the Earth's south pole. And then we have 2 circles. The celestial equator is a projection of the Earth's equator into space, and it makes a complete circle around the celestial sphere. And then the ecliptic, which we briefly mentioned last week. So go back and look at that video if you want a refresher. Remember, the ecliptic is the path of the sun the path the sun follows as it appears to circle around the celestial sphere once each year. It crosses the celestial equator at a 23.5-degree angle because that is the tilt of the Earth's axis. Then we have the band of light that we call the Milky Way that circles all the way around the celestial sphere, passing through more than a dozen constellations. The widest and brightest parts of the Milky Way are most easily seen from the southern hemisphere, which probably explains why the Aborigines of Australia are one of the only cultures who gave names to patterns within the dust lanes of the Milky Way rather than just the patterns of the stars of the Milky Way. And our Milky Way Galaxy gets its name from this band of light, and the 2 Milky Ways are obviously one and the same. The Milky Way in the night sky traces our galaxy's disk of stars, the galactic plane, as it appears from our location within the Milky Way Galaxy. So as you can see here in this beautiful image from the European Space Agency, our galaxy is shaped like a thin pancake with a bulge in the middle. We view the universe from our location a little more than halfway out from the center of this pancake. And in all directions that we look within the pancake, we see the countless stars and vast interstellar clouds that make up the Milky Way in the night sky. That is why the band of light makes a full circle around the sky. The Milky Way appears somewhat wider in the direction of the constellation Sagittarius because that is the direction in which we are looking toward the galaxy's central bulge. We have a clear view to the distant universe only when we look away from the galactic plane, along directions that have relatively few stars and clouds to block our view. So if you want to look away from the galactic plane, you can either look behind us, where there's definitely much less. There's still dust and stars in the way, but there's much less, so we look behind us, or look above the plane of the galaxy. The dark lanes that obscure the center of the galaxy are the densest clouds. In fact, those clouds really kind of stop us from seeing anything in our galaxy more than a few thousand light years into the disk. As a result, much of the galaxy remained hidden from view until we invented telescopes that can collect the light that passes through the dust, such as infrared, X-ray, and radio. So that's kind of an introduction to the Milky Way. Now, if you were, like I keep suggesting you go do, if you were to go out tonight and look at the night sky, you would not see the celestial sphere. What you would actually see is your local sky. The sky is seen from wherever you happen to be standing, and it appears to take the shape of a hemisphere or dome, which explains why people of many ancient cultures, and sadly, still including some people today, imagine that we lived on a flat Earth under a great dome encompassing the world. The dome shape arises from the fact that we see only half of the celestial sphere at any particular moment from any particular location, while the ground blocks the other half from view. So if you look in this figure, there are a couple of key points to note. So hopefully you're familiar with the concept of the horizon. That is the boundary between the Earth and sky. The point directly overhead your head is the zenith. Everyone has their own different zeniths. The meridian is an imaginary circle outlined here in a nice pink magenta. It's a half circle stretching from the horizon due south through the zenith to the horizon due north. And we can pinpoint the location of any object in the local sky by stating its direction along the horizon. You might hear this sometimes be called an azimuth, but we'll call it direction. It's degrees clockwise from due north, but we'll just say northeast, south, and west. And then the altitude above the horizon measured in degrees. So for example, in this figure, this person is pointing at a star that is at 60 degrees southeast. Note that the zenith has an altitude of 90 degrees, but no direction because it is straight overhead. So here is tonight's night sky. And you can see I point out some of the brightest stars and one planet to talk about how we would talk about the direction. So we would say something like Arcturus is east at 10 degrees. Capella is west at 60. Mars is west at 30 degrees. Sirius is south at 30 degrees. I know the degrees because each of these green completed circles is 10 degrees of altitude. So I just counted up which one is it closest to. So we do still have a problem because we have no depth perception on the celestial sphere. That means we have no way to judge true sizes or separations of the objects we see in the sky. However, we can describe the angular sizes or separations of objects without knowing how far away they are. So the angular size of an object is the angle it appears to span in your field of view. So for example, the angular sizes of the sun and moon are both about half a degree. Note that the angular size does not by itself tell us an object's true size because angular size also depends on distance. So for example, I told you the angular size of the sun and moon is both about half a degree, but the sun is about 400 times as large in diameter as the moon, but it has the same angular size because it is also about 400 times further away. Then we also talk about angular distances, and that is the distance between a pair of objects in the sky is the angle that appears to separate them. So for example, the angular distance between the stars at the end of the Big Dipper's ball, I'm sorry, I mislabeled this diagram here. So between these two stars, Dubhe and Merak, is about 5 degrees. And the angular length of the Southern Cross, if you're in the Southern Hemisphere, is about 6 degrees. You can use your outstretched hand to make some rough estimates in the sky. For greater precision, we subdivide each degree into 60 arc minutes and each arc minute into 60 arc seconds. So in a single degree, there are 60 arc minutes or 3,600 arc seconds. So for example, if I wanted to calculate the angular separation between Betelgeuse and Rigel, the two brightest stars in Orion, I would say that Betelgeuse and Rigel are 18 degrees, 36 arc minutes, 22 arc seconds apart. All right, so that's how you kind of measure things on the sky. Now let's talk about some motion. So the first question we want to know is, why do stars rise and set? Which you'll definitely notice if you just spend a few hours underneath a starry sky. You'll notice that the universe seems to be circling around us, with stars moving gradually across the sky from east to west. Many ancient peoples took this appearance at face value, concluding that we lie at the center of a universe that rotates around us each day. Obviously, today we know that the ancients had it backward. It is the Earth that rotates daily, not the rest of the universe. But we can picture the movement of the sky by imagining the celestial sphere rotating around the Earth, like in this figure. From this perspective, you can see how the universe seems to turn around us. Every object on the celestial sphere appears to make a simple daily circle around Earth. However, the motion could look a little more complex in the local sky because the horizon cuts the celestial sphere in half. So this figure shows the idea for a typical northern hemisphere location, about a latitude of 40 degrees north. If we study this figure carefully, we'll notice the following key facts about the paths of various stars in the night sky. But first, I think it'll be easier for us to understand this figure if we rotate it to where the ground is flat. So now we have the zenith straight up. The north celestial pole is up at an angle, and obviously we can't see the south celestial pole. So hopefully you can come to these three facts: that stars near the north celestial pole are circumpolar, always remaining above the horizon, circling counterclockwise around the north celestial pole each day. Those are these stars that their pink arrows never go below the horizon. Excuse me. Stars near the south celestial pole never rise above the horizon at all. So if this white arrow that goes near the south celestial pole, notice that the arrow never comes above the horizon. Those are circumpolar for the south celestial pole. And then all other stars have daily circles that are partly above the horizon and partly below it, which means they appear to rise in the east and set in the west. Those would be, for example, this circle. Notice how it's white when it goes below the horizon, pink when it comes above the horizon. So if you take a look at photographs like this is a time exposure photograph. You can see the daily part of the daily paths of stars. So paths of circumpolar stars are visible here. I've hopefully tried to circle most of them in red. Anything inside this red circle is a circumpolar star for the south celestial pole, since this image was taken at the Atacama Desert in Chile, which is in the southern hemisphere. All the other stars are not circumpolar because they will set below the horizon and rise above the horizon at some point. And then notice that we can't even see the north celestial pole. So any of those circumpolar stars will never be visible from Chile. That's kind of the idea of why stars rise and set. However, if you stay in one place, the basic patterns of motion in the sky will stay the same from night to night. However, if you travel far north or south, you'll see a different set of constellations than you see at home. And even if you stay in one place, you'll see different constellations at different times of year. So let's explore that a bit. Let's explore those answers. So in case you forgot, the sky does vary with latitude, and latitude measures the north-south position on Earth, and longitude measures the east-west position. So latitude is defined to be 0 degrees at the equator, increasing to 90 degrees north at the North Pole and 90 degrees south at the South Pole. By international treaty, longitude is defined to be 0 degrees along the prime meridian, which passes through Greenwich in the United Kingdom. Stating a latitude and longitude pinpoints a location on Earth. So for example, Atlanta, Georgia is at there roughly 34 degrees north and 84 degrees west. Where I'm at in Cleveland, Ohio, it's significantly further north, 42 degrees north, but just a little bit eastward at 82 degrees west. Latitude affects the constellations we see because it affects the locations of the horizon and the zenith relative to the celestial sphere. So you can see these two figures kind of shows how this works for the latitude of the North Pole, the one on top, and for Sydney, Australia at 34 degrees south of the bottom. Note that although the sky varies with latitude, it does not vary with longitude. For example, Charleston, South Carolina, and San Diego, California are at about the same latitude. So people in both cities will see the same set of constellations each night. For example, at the North Pole, you can see only objects that lie on the northern half of the celestial sphere, and they are all circumpolar. That is why the sun remains above the horizon for 6 months of the North Pole. The sun lies north of the celestial equator for half of each year. So during these 6 months, it circles the sky at the North Pole just like a circumpolar star. These diagrams hopefully also show you a very important fact for navigation. And that fact is that the altitude of the celestial pole in your sky is equal to your latitude. So, for example, if you see the north celestial pole at an altitude of 40 degrees above your north horizon, your latitude will then be 40 degrees north. Similarly, if you're, say, in Sydney, Australia, and you see the south celestial pole at an altitude of 34 degrees above your south horizon, your latitude is 34 degrees south. You can therefore determine your latitude simply by finding the celestial pole in your sky. So for us here in the northern hemisphere, that's very easy. You just got to find the star Polaris, which is at the end of the handle of the Little Dipper. In the southern hemisphere, you've got to use the Southern Cross. So here I've got the night skies for both myself here in Cleveland and for people in Atlanta. And you can see I've circled the star Polaris. And you notice that it's at different altitudes, as it should be. Because remember, Cleveland and Atlanta are different latitudes. Cleveland is at a latitude of 42 degrees north, so Polaris can be seen 42 degrees above the northern horizon. Atlanta is located at 34 degrees north, so you can see Polaris at an angle of 34 degrees above the north horizon. You can do this all over the world. You will always be able to find your latitude. Your longitude is a much more difficult problem, and I will not be talking about that. All right, so that's how variation with latitude works. Now we got to move on to variation with time of year. But before we do that, if you were joining us on Zoom, then I would have put in a poll on the Zoom. But since you're watching this on video, I'll read the questions out and then pause. I do want you to think about and have an answer for these questions. So, first question: Beijing and Philadelphia have about the same latitude but different longitudes. Therefore, tonight's night sky in these two places will A, look about the same, B, have completely different sets of constellations, or C, have partially different sets of constellations. And the next one is true or false. The constellation Orion didn't exist when my grandfather was a child. So go ahead and pause the video and come back, and I'll tell you the answers. All right, so the answer to the first one is A. They'll look about the same. Remember, constellations only vary with latitude, not longitude. Since Beijing and Philadelphia are roughly at the same latitude, then they will have the same constellations. And then the constellation Orion didn't exist when my grandfather was a child. That is false. Although the International Astronomical Union only officially defined the constellation in 1928, depending on how old your grandfather is. That constellation has been recognizable since the ancient Greeks, and that pattern of stars has been up there since before the ancient Greeks. So any way you think about it, that statement is false. All right, so now let's move on to variation with time of year. So the night sky changes throughout the year because of the Earth's changing position in its orbit around the sun. So this figure kind of shows how it works. From our vantage point on Earth, the annual orbit of Earth around the sun makes the sun appear to move steadily eastward along the ecliptic, with the stars of different constellations in the background at different times of year. The constellations along the ecliptic make up what we call the Zodiac. Tradition places 12 constellations along the Zodiac, but the official borders include a 13th constellation named Ophiuchus. The sun's apparent location along the ecliptic determines which constellations we see at night. So for example, in this figure, it shows that the sun appears to be in Leo in late August. So here's Earth on August 21st, follow the day line through the sun to the stars, and so the sun will appear to be in Leo. Therefore, we cannot see Leo at this time because it is in our daytime sky. And as I continually advise you not to do, please do not stare at the sun. But if we follow the night side, then the night is Aquarius. So we'll be able to see Aquarius all night long because of its location opposite Leo in the sky. 6 months later, in February, the opposite will be true. Following the day era, we'll be able to see the sun will be in Aquarius, and we will be able to see Leo all night long. So this brings me just briefly to astrology. So here's the night sky, or the daytime sky, for March 7th. According to astrology, the sun is supposed to be in Pisces. People born around March 7th are given the zodiac sign of Pisces, but the sun is actually in Aquarius. So what gives? Well, it's because all the astrological signs were created thousands of years ago when the sun actually was in Pisces in March, but now the sky has shifted. So for example, here's the daytime sky for my birthday on June 14th. My astrological sign is a Gemini, but the sun is clearly within the borders of the constellation Taurus. So we'll talk more about this, about astrology next week, oddly enough, when we talk about the history of astronomy. But I just want to get the point across that astrology is not astronomy. The two are not the same, although they do use the same stars. If you're interested, I went ahead and looked at where the sun will be each day of the year. Aside from adding in Ophiuchus as a zodiac constellation, nothing else has really changed. You're not a Capricorn, the constellation name is Capricornus. You're not a Scorpio, the constellation is Scorpius. And to give a general help, find the zodiac that you currently know and go to the one above it. That's generally what your true zodiac sign is. So mine's the one above it. I'm actually a Taurus. The only big difference is the sun doesn't spend much time in Scorpius. It spends about 5 days in Scorpius. Most of the time that Scorpius traditionally has been given to Ophiuchus. So if you were a Scorpio, you're probably actually born under the constellation of Ophiuchus. like I said, we'll talk more about astrology next week. So now we've seen how the Earth's rotation makes the sky appear to circle us daily and how the night sky changes as Earth orbits the sun each year. And the combination of Earth's rotation and the orbit also leads to a progression of the seasons. So obviously, hopefully you don't need me telling you this, but we have seasonal changes, such as longer and warmer days in the summer and shorter and cooler days in the winter. But why do those seasons occur? The answer is that the tilt of Earth's axis causes sunlight to fall differently on Earth at different times of year. So this figure hopefully illustrates many of the key ideas. So the Earth's axis remains pointed towards the same direction in space, towards Polaris, throughout the year. As a result, the orientation of the axis relative to the sun changes over the course of each orbit. The northern hemisphere is tipped toward the sun in June and away from the sun in December, while the reverse is true for the southern hemisphere. That is why the two hemispheres experience opposite seasons. The rest of the figure shows how the changing angle of sunlight on the two hemispheres leads directly to seasons. So if you look at the Earth on the left at the June solstice, the axis tilt is causing sunlight to strike the northern hemisphere at a steeper angle and the southern hemisphere at a shallower angle. That steeper sunlight angle makes it summer in the northern hemisphere for two reasons. So first, the steeper angle means more concentrated sunlight, which tends to make it warmer. Second, if you visualize what happens as Earth rotates each day, you'll see that the steeper angle also means the sun follows a longer and higher path through the sky, giving the northern hemisphere more hours of daylight, during which it is warmed by the sun. The opposite is true for the southern hemisphere. The shallower sunlight angle makes it winter there because sunlight is less concentrated and the sun follows a shorter, lower path through the sky. But that sunlight angle will gradually change as the Earth orbits the sun. So on the opposite side of Earth's orbit, at the December solstice on the right side of this figure, it's become winter for the northern hemisphere and summer for the southern hemisphere. In between these two extremes, the hemispheres are illuminated equally in March and September. It is therefore spring for the hemisphere that is on the way from winter to summer and fall for the hemisphere that is on the way from summer to winter. So we are marking four different points here. Hopefully you're familiar with this already just by living on Earth. But in case you aren't, on the left is the June solstice. And that's the moment around June 21st. And that's the moment when the northern hemisphere is tipped most directly toward the sun and receives the most sunlight. On the opposite side is the December solstice, occurring around December 21st. And it's the moment when the northern hemisphere receives the least direct sunlight. And in between, we have the March equinox, happens around March 21st, and is the moment when the northern hemisphere goes from being tipped slightly away from the sun to being tipped slightly toward the sun. And then the September equinox, which occurs around September 22nd, and is the moment when the northern hemisphere first starts being tipped away from the sun. So the exact dates and times of the solstices and equinoxes can vary up to a couple of days from those dates I just gave, depending on where we are in the leap year cycle. In fact, our modern calendar includes leap years specifically to keep the solstices and equinoxes at roughly the same dates. All right. But you may be wondering, why haven't I not talked about the orbital distance affecting the seasons? Well, it's kind of, first of all, what you may expect is not what's actually happening. It's kind of backwards from common notion. We would think that we're closest to the sun in the summer, furthest from the winter. Actually, it's backwards. We are the furthest from the sun during the summer, which you can see here. July 3rd marks the aphelion, means furthest from the sun. And we're closest to the sun during the middle of January, around January 3rd. It's the perihelion. So what the heck is happening here? Why aren't the seasons affected by how close the Earth is to the sun? The main reason for this fact becomes clear when you look at a map of the Earth like that there at the bottom. Most of Earth's land lies in the northern hemisphere, with far more ocean in the southern hemisphere. So as you'll notice at any beach, lake, pond, or pool, water takes longer to heat or cool than soil or rock. The water temperature therefore remains fairly steady both day and night, while the ground can heat up and cool down dramatically. The southern hemisphere's larger amount of ocean moderates its climate. So the northern hemisphere, with more land and less ocean, heats up and cools down more easily, which is why it has the more extreme seasons. And our orbital distance from the sun, it doesn't vary that much, maybe about 2 or 3%. You can see In January, we're only 147 million kilometers compared to in July, where it's 152 million kilometers. That's not a big difference there. So yeah, that's why the orbital distance does not affect the seasons. All right, so moving on, that's how the sky moves. But aside from the sun, the moon is the brightest and most noticeable object in our sky. The moon is our constant companion in space, traveling with us as we orbit the moon. And as the moon orbits the Earth, as we orbit the sun, so as the moon orbits the Earth, it returns to the same position relative to the sun in our sky, about every 29 and a half days. This time period marks the cycle of the lunar phases, in which the moon's appearance in our sky changes as its position relative to the sun changes. This 29 and a half day period is also the origin of the word month. So you can think of month instead of month. So the first step in understanding these lunar phases is to recognize that sunlight essentially comes at both the Earth and the moon from the same direction. So you can see here, if we go back to our scale model of the solar system, remember we shrank the sun to the size of a grapefruit, and we placed it at the center of Centennial Olympic Park, at the center of those fountains in the middle ring. On our scale, the Earth and the moon are about 15 meters away from the sun. That's that black circle. It's the orbit of the Earth. On this scale, the moon is about 4 centimeters away from Earth, which it probably varies depending on person, but 4 centimeters is about the width of my 3 middle fingers put together. On this scale, if you were to go to Centennial Olympic Park and put down something for the moon, that tiny little circle is the orbit of the moon around the Earth. So very, very tiny there. So that means essentially sunlight is coming to the Earth and the moon from the same angle. We see lunar phases because half of the moon is always illuminated by the sun, but the amount of this illuminated half that we see from Earth depends on the moon's position in its orbit. So here you see how those phases work. The moon's phase also determines the times of day at which we see it in the sky. So for example, the full moon must rise around sunset because it occurs when the moon is opposite the sun in the sky. It therefore reaches its highest point in the sky at midnight and sets around sunrise. Similarly, the first quarter moon must rise around noon, reach its highest point around sunset, and set around midnight because it occurs when the moon is about 90 degrees east of the sun in our sky. So notice that the phases from new to full are said to be waxing, which means increasing, while the phases from full to new are waning or decreasing. Also notice that no phase is called a half moon. Instead, we see half the moon's phase at first quarter and third quarter phases. These phases mark the times when the moon is 1/4 or 3/4 of the way through its monthly cycle. The phases just before and after a new moon are called crescent, while those just before and after a full moon are called gibbous. A gibbous moon is essentially the opposite of a crescent moon. The term gibbous literally means humpback, so you can probably see how the gibbous moon got its name. And although we see many phases of the moon, we do not see many faces. On Earth, we always see the same face of the moon. This happens because the moon rotates on its axis in the same amount of time it takes to orbit Earth, which is called synchronous rotation. And then a good way to solidify your understanding of the lunar phases is to imagine that you live on the side of the moon that faces the Earth. For example, what would you see if you looked at Earth when people on Earth saw a new moon? By remembering that a new moon occurs when the moon is between the sun and the Earth, you'll realize that from the moon, you'd be looking at Earth's daytime side and hence would see a full Earth. Similarly, at full moon, you'd be facing the night side of Earth and would see a new Earth. So in general, you'll always see Earth in a phase opposite the phase of the moon, seen by people on Earth at the same time. So here's a little animation to kind of show you. We're going to start this animation in first quarter. So on the bottom panel, on the left, you can see the view of Earth from the moon. Then the center, you see the moon going around in its orbit. And then on the right, you can see the view of the moon from Earth. So we're going to start off in first quarter moon. Now, as the light widens, we're now in waxing gibbous. And then as we come behind the Earth, right about here, we're at full moon because the Earth is between the moon and the sun. And now as we get out from behind the Earth, we're going to go into waning gibbous. This is right now. All right, right about here, we're at a third quarter moon. And as soon as we leave third quarter, we're going to go into waning crescent until the moon comes between the Earth and the sun right about now. So now we're at new moon. You would not be able to see the moon in the sky because it would be very near the sun. And once again, please do not go look at the sun directly. And now we're in waxing crescent, and we're going to come right back around into first quarter. So that's how the lunar phases work. So occasionally, the moon's orbit around Earth causes events much more dramatic than just the simple lunar phases. The moon and the Earth both cast shadows in sunlight, and these shadows can create eclipses when the sun, Earth, and moon fall into a straight line. So eclipses come in two types. We've got a lunar eclipse when the Earth lies directly between the sun and the moon, so Earth's shadow falls on the moon. Oh, excuse me. And a solar eclipse when the moon lies directly between the sun and the Earth, so the moon's shadow falls on the Earth. But note that because Earth is much larger than the moon, Earth's shadow can cover the entire moon during a lunar eclipse. Therefore, a lunar eclipse can be seen by anyone on the night side of Earth when it occurs. In contrast, the moon's shadow can cover only a small portion of Earth at any one moment, so you must be living within the relatively small pathway through which the shadow moves to see a solar eclipse. That's why you see lunar eclipses more often than solar eclipses, even though both types occur about equally often. So, obviously eclipses don't happen every single month, so what are the conditions necessary for these eclipses to happen? So, the missing piece of the story of why they don't happen every month is because, and you may have noticed this in the little animation a few slides ago, is that because the moon's orbit is slightly inclined by about 5 degrees to the ecliptic plane. Remember, that's the plane that the Earth orbits the sun around. So to visualize this inclination, let's imagine the ecliptic plane as the surface of a pond, as you can see here. Because of the inclination of its orbit, the moon spends most of its time either above or below the surface of the water. It crosses through this surface only twice during each orbit. You can see 1 point over here, 1 point over here. Similarly, 1 point here, 1 point here. Anytime the white arrows cross the orange circle. It crosses through the surface only twice during each orbit, once coming out and once going back in. The 2 points in each orbit at which the moon crosses the surface are called the nodes of the moon's orbit. And notice that the nodes are aligned approximately the same way throughout the year. Diagonally here, like this, like this, like that. Which means they lie along a nearly straight line with the sun and the Earth about twice each year. Eclipses can occur only during these periods because these are the only times when the moon can be directly in line with the sun and the Earth. In other words, eclipses only occur when the phase of the moon is full for a lunar eclipse or new for a solar eclipse, and the new or full moon occurs at a time when the moon is very close to a node. So a new moon near the node, a solar eclipse, full moon near the node, a lunar eclipse. Similarly, it can happen over here as well. Let's see, note that while this figure shows just kind of these basic shadow cones, if we look at the geometry in a closer look, you'll see that each of those shadows consists of 2 distinct regions. We have a central umbra, where sunlight is completely blocked, and a surrounding penumbra, where sunlight is only partially blocked. Lunar and solar eclipses vary in appearance depending on which part of the shadow is involved. So let's talk about lunar eclipses first. A lunar eclipse begins at the moment when the moon's orbit first carries it into the Earth's penumbra. After that, we will see one of 3 types. If the sun, Earth, and moon are nearly perfectly aligned, the moon passes through the Earth's umbra and we see a total lunar eclipse. If the alignment is somewhat less perfect, only part of the full moon passes through the umbra with the rest in the penumbra, and we see a partial lunar eclipse. If the moon passes through only Earth's penumbra, we see a penumbral lunar eclipse, which is the most common. But they're also the least visually impressive since the moon only darkens slightly. Total lunar eclipses are the most spectacular. The moon becomes dark and eerily red during totality when the moon is entirely engulfed in the umbra. So to understand how that redness occurs, Consider the view of an observer on the eclipsed moon, who would see the Earth's night side surrounded by the reddish glow of all the sunrises and sunsets occurring on the Earth at that moment. It is that reddish light that illuminates the moon during a total eclipse. And I have a little video here of the January 2018 lunar eclipse, total lunar eclipse from LA. And you can see it start to darken there on the left. And as it enters more fully into the Earth's shadow, the redness will start to appear. And there's that kind of eerie reddish glow. Now, in this particular video, the moon started to set as the eclipse was still going on, which can happen. So you'll see it duck behind a mountain in a moment. There it is. But still absolutely beautiful to watch. When it comes to, and here's different images of what each of the types of lunar eclipses look like. So you see the red total, half shadowed partial, and the barely darkened penumbral lunar eclipse. When it comes to solar eclipses, we also see three types there as well. If a solar eclipse occurs when the moon is in a part of its orbit where it is relatively close to the Earth, the moon's umbra can cover a small area of Earth's surface. Within this area, you will see a total solar eclipse. If the eclipse occurs when the moon is in a part of its orbit that puts it farther from Earth, the umbra may not reach Earth's surface, leading to an annular eclipse where you see a ring of sunlight surrounding the moon. And that will be in the region of Earth directly behind the umbra. In either case, the region of totality or annularity will be surrounded by a much larger region that falls within the moon's penumbral shadow, resulting in a partial solar eclipse, in which only part of the sun is blocked from view. The combination of Earth's rotation and the moon's orbital motion causes the moon's shadow to race across the face of the Earth at a typical speed of about 1,700 kilometers per hour. As a result, the umbral shadow traces a narrow path across Earth, and totality never lasts for more than a few minutes in any particular place. Obviously, a total solar eclipse is a spectacular sight. If you have a chance to see one, definitely go see one. Hopefully, many of you were able to see the Great American Solar Eclipse in 2017, which this is a video of. The official Celestron Maker of Telescopes video. So you can see the moon start to take a bite out of the wheel of cheese that is the sun. Happens very fast, only a few minutes. When it comes to predicting eclipses, few phenomena have so inspired humans throughout the ages as those eclipses. For many cultures, eclipses were mystical events associated with fate or the gods, and countless stories and legends surround them. One legend holds that the Greek philosopher Thales successfully predicted the year, but presumably not in the exact time, that a total solar eclipse would be visible in the area where he lived, which is now part of Turkey. The eclipse occurred as two opposing armies, the Medes and the Lydians, were massing for battle, and it so frightened them that they put down their weapons, signed a treaty, and returned home. Because modern research shows that the only eclipse visible in that part of the world at about that time occurred on May 28th, 585 BCE. We know the precise date on which the treaty was signed, the earliest historical event that can be dated precisely. Much of the mystery of eclipses probably stems from the relative difficulty of predicting them. Remember those two periods, the eclipse seasons, in which the nodes of the moon's orbit are closely aligned to the sun. Each eclipse season lasts a little less than 5 weeks, which means there's generally one lunar eclipse at full moon and one solar eclipse at new moon during each eclipse season. Because the eclipse season is slightly longer than the cycle of phases, there can occasionally be a third eclipse during a single eclipse season. But if that was the whole story, then we would see eclipses every 6 months. But actual prediction is more difficult than this because of something the figure that we saw earlier does not show. Those nodes move slowly around the moon's orbit, which is called the precession of the nodes. And it has a period of 18.6 years, which causes the eclipse seasons to occur slightly less than 6 months apart, about every 173 days. And so the combination of the changing dates of the eclipse seasons and the 29.5-day cycle of lunar phases makes eclipses recur in a cycle of about 18 years and 11 1/3 days, called the Saros cycle. Astronomers in many ancient cultures were able to identify the Saros cycle and use it to make predictions. So, for example, the Babylonians in the Middle East achieved remarkable success at predicting eclipses more than 2,500 years ago. And the Mayans achieved similar success in Central America. In fact, the Mayan calendar includes a cycle of 260 days, almost exactly 1.5 times the 173 days between successive eclipse seasons. Nowadays, we know the orbital motions of the Earth and the Moon exactly. So here's a list of eclipses visible in the United States for the remainder of the decade. So tons of lunar eclipses, some visible for part of us, some visible for all of us. The next total lunar eclipse that will be visible for the entire United States will be in the middle of March of 2025. However, for those of you on the Western United States, you'll be able to get a total lunar eclipse in May, in just a few months. So keep an eye out for that. When it comes to solar eclipses, there will be only two that will be visible, two big ones that will be visible for the people in the United States. There's an annular solar eclipse on October 14th, 2023. You can see the path through which, the path it will take across the United States. So just south of Portland, people in San Antonio, Texas will be in a prime position to watch this annular solar eclipse. And then there's a total solar eclipse on April 8th in 2024 that crosses through much of the rest of the country. So going up from Austin through Dallas and Texas, crossing Indianapolis, crossing, yes, Cleveland, and then up into upstate New York and then into Maine. So you're all welcome to come to my apartment in 2024. I don't know how many of you will fit in my apartment, but certainly Cleveland will be the place to be in a few years. All right, so we've now, here's another question. Once again, I put this in a poll in Zoom, but I'll read the question, and since you're watching the video, pause it and think about it. So if there's going to be a total lunar eclipse tonight, then you know that A, the moon's phase is full, B, the moon's phase is new, or C, the moon is unusually close to Earth. All right, I assume you unpaused the video now. The correct answer is A, the moon's phase will be full. Remember, the moon has to be on the opposite side of the Earth from the sun, which means it's getting all the sunlight, so it'll be full. All right, so we've covered the appearance and motion of the stars, sun, the moon, and the sky, and that leaves us with just the planets. As you'll soon see, planetary motion posed an ancient mystery that played a critical role in the development of modern civilization. So 5 planets are easy to see with the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. Mercury is visible somewhat infrequently after sunset or just before sunrise because it is so close to the sun. Venus shines brightly in the early evening in the west or before dawn in the east. So if you see a very bright star in the early evening or early morning, it's probably Venus and not actually a star. Don't waste your wish on that one. Jupiter, when it is visible at night, is the brightest object in the sky besides the moon and Venus. Mars is often recognizable by its reddish color, though you should probably check an app on your phone to make sure you aren't looking at a bright red star. And Saturn is also easy to see with the naked eye, but because many stars are just as bright as Saturn, it helps to know where to look, once again, using that app on your phone. You've seen this image that I took from a planetarium software, a gathering of all five naked eye planets that happened on April 23rd, 2002. The next time the planets will do anything like this will be in September of 2040. So if you didn't see this, you got to wait a little bit while. And over the course of a single night, the planets do behave like all the other objects in the sky. Earth's rotation makes them appear to rise in the east and set in the west. But if you watch those planets night after night, you'll notice that their movements among the constellations are complex. Instead of moving steadily eastward relative to the stars like the sun and the moon, the planets vary substantially in both speed and brightness. In fact, the word planet comes from a Greek word meaning wandering star. Moreover, while the planets usually move eastward through the constellations, they occasionally reverse course, moving westward through the zodiac. These periods of apparent retrograde motion last a few weeks to a few months, depending on the planet. And for ancient people who believed in an Earth-centered universe, apparent retrograde motion was very difficult to explain. After all, what can make the planets sometimes turn around and go backward if everything moves around circles around the Earth? The ancient Greeks came up with some very clever ways to explain it, but their explanations, which we'll explore next week, were pretty dang complex. In contrast, apparent retrograde motion has a simple explanation in a sun-centered solar system. So here is the actual apparent retrograde motion of Mars in late 2009, early 2010. And I've labeled the points according to this diagram. So yellow circle is the sun. The points labeled T and a number are the Earth. The points labeled P and a number are Mars. And then the points labeled A and a number are what we see on the night sky. So here, as Earth approaches Mars in its orbit around the sun, in both their orbits around the sun, connect that line and we see A1. Perfectly fine. And Mars will continue moving eastward until point 2, where we're looking through Mars, and yes, it's still eastward. But now as Earth begins to catch up to Mars in its orbit, then looking through the points labeled 3, Mars will move backwards. And then as Earth passes Mars, we'll look even further backwards. But as Mars moves along its orbit and the Earth moves back on the other side of the sun, Mars will move to point 5. Note that Mars never actually changes direction. Mars is always orbiting from 1 to 5. It only appears to go backward as Earth passes Mars in its orbit. So that brings up the question. So why did the ancient Greeks reject this way? This is pretty simple to understand. Technically, the idea that the Earth goes around the sun was suggested as early as 260 BCE by the Greek astronomer Aristarchus, but his contemporaries rejected that idea, and the sun-centered solar system did not gain wide acceptance until almost 2,000 years later. And although there were many reasons the Greeks were reluctant to abandon the idea of an Earth-centered universe, one of the most important was their inability to detect what we call a stellar parallax. So this is a thing you can do right now as you're listening to this video. So I want you to extend your arm and hold up your thumb. If you keep your fingers still and alternately close and open your left and right eye, keep winking at your thumb, you'll see your thumb move back and forth against the background objects of your room. This apparent shift is called parallax, and it occurs because your two eyes view your finger from opposite sides of your nose. So if you move your finger closer to your face, the parallax increases. And if you were to look at a distant object on your wall, instead of your finger, you may not notice any parallax at all. Certainly if you look out your window at a distant tree, you'll certainly not notice it. In other words, parallax depends on distance, with nearer objects exhibiting greater parallax than more distant ones. So if you now imagine that your two eyes represent Earth at opposite sides of its orbit around the sun, and then the tip of your finger represents a relatively nearby star, like you see in this figure, you have the idea of stellar parallax. Because we view the stars from different places in our orbit at different times of year, nearby stars should appear to shift back and forth against the background of more distant stars. Because the Greeks believed that all stars lie on the same celestial sphere, they expected to see stellar parallax in a slightly different way. If Earth orbited the sun, they reasoned, at different times of year, we would be closer to different parts of the celestial sphere and would notice changes in the angular separation of stars. However, no matter how hard they searched, they could find no sign of stellar parallax. So they concluded that one of the following must be true. Either the Earth orbits the sun, but the stars are so far away that stellar parallax is undetectable to the naked eye, or there is no stellar parallax because the Earth remains stationary at the center of the universe. Guess which one's the Greek picked? Aside from Aristarchus, the Greeks picked the wrong answer, the second one, because they could not imagine that the stars could be that far away. Today, we can detect stellar parallax with the aid of telescopes, providing direct proof that Earth really does orbit the sun. Careful measurements of stellar parallax also provide the most reliable means of measuring distances to nearby stars. So the ancient mystery of the planets drove much of the historical debate over Earth's place in the universe. In many ways, the modern technological society we take for granted today can be traced directly to the scientific revolution that began in the quest to explain the strange wanderings of the planets among the stars in our sky. And we will return our attention to this revolution next week. So we just finished the night sky. Next week, we will talk briefly about the history of astronomy and what science really is. So thank you for joining me.